Okay, let's continue our next lecture for superposition of basic plane potential flow. Basically, in previous lecture, we focused our lecture on basic plane potential flow. Okay, so there are four types of basic plane potential flow, which is uniform flow, and then source and sink, vortex, and the last one is doublet. Okay, so for the doublet, we call it as a doublet when source and sink approach one another, so that there was a doublet. Okay, so for this superposition of plane potential flow, superposition of basic plane potential flow. Okay, so for this superposition, it is a combination between the basic plane potential flow. Okay, for example, it is a combination between uniform flow and source. The first one is uniform flow and source superposition. One is uniform flow plus source, and then the second one, it is Rankine oval, which is uniform flow plus the equal strength of source and sink. Okay, and then the last one, it is for flow over cylinder. Okay, so for the flow over cylinder, it is a uniform flow plus with doublet. Okay, so doublet, recall the definition of doublet is when source and sink approach one another. So this one we call it as a doublet. Okay, so there was a superposition for basic plane potential flow. Okay, but before that, let's recall for the plane potential flow. So it is basically governed by a Laplace equation. So for the potential flow, it is governed by Laplace equation. So it is a linear. So it was a linear partial differential equation. Okay, so just recall that your Laplace equation is the square psi over del x square plus d square psi over dy square plus d square phi over dz square, or it is del square dot with phi, which is velocity potential. Okay, and then just recall that for the stream function, okay, let's say we have this stream function. Okay, so stream function 1, stream function 2, and stream function 3. So stream, you will have stream function, and then of course you will have streamline 1 and streamline 3. Okay, so from previous lecture we know that flow cannot passing through this streamline. Okay, so flow will not passing through this streamline. Okay, so the flow only flow between this streamline. Okay, so this is where the flow will flowing parallel between the streamline. Okay, so that's why for the various basic plane potential flow, when we combine with stream function, it can form a new potential and stream function. Okay, so as I mentioned, any streamline in an inviscid flow, so for the inviscid flow can be considered as a solid boundary. Okay, so this will be considered as a solid boundary. Okay, can be considered as a solid boundary. Okay, solid boundary mean that flow, no radial flow passing will passing through the solid boundary or streamline. Okay, and then since the condition along solid boundary and a streamline are the same, which is no flow through the boundary or streamline. Okay, so that is for basic not a basic there is some we recall what we had learned in previous lecture. Okay, so today we start with superposition for uniform flow plus with source. Okay, so this lecture focus for uniform flow plus with source. Okay, but before that, let's watch this video so that you have an idea what is superposition, and then what happen when you have a uniform flow, and then you have a source and in between your uniform flow. So what happened to your flow? Okay, so let's watch this video. Okay, so this is your uniform flow. Okay, so this is your uniform flow. Okay, so this is your source. Okay, and then after we release the source, release the inject from the bottom of this container, so the flow will be like this. Okay, so this is source, this is where the source coming from, and then there are okay, let I pause this. So there are some distance between the point or the source and also this point. Okay, so for this point we call it as a stagnation point. Okay, so let's remember that point in front of the source point, it is called as a stagnation point. So in this lecture I will explain how to determine the stagnation point for the source for this kind of uniform flow, and also combined with source. Okay, so this is how it looks like. Okay, so this is like a body. Okay, so this is your streamline. Okay, and then flow through your streamline, and then this will be acting as a solid body. Okay, so as you can see, no streamline in this inside this solid body. Okay, this is where we turn off the power or the source for this inject. Okay, so it will be purely uniform flow. Okay, so now let's move to our to the slide. Okay, so since it is a combination between uniform flow and source, okay, so let's from the video you can see there are we have this U, which is a uniform flow. Okay, so U is a uniform flow coming from the left to the right, and then this is a source where we start the source. Okay, we start the source, and then this is where the stagnation point. Okay, so the distance from point for the source to the stagnation point we call it as a B. Okay, and then since it is a source, so we have the radial. We need to have radial velocity. Okay, so for the stream function, okay, so stream function for stream function of uniform flow plus stream function for the source. Okay, so let just recall your previous note. For the uniform flow, it is stagnation. For the psi for the uniform flow. Okay, psi for uniform flow is basically uy. Okay, so uy, so y basically equal to r sine theta when we want, if we want to define in terms of this is basically y. Okay, when we want to define in terms of cylindrical polar coordinate system, and then plus with m over 2 pi. Okay, m over 2 pi theta. So this one will, it is psi for the for the source. Okay, psi for the source, and then the corresponding velocity potential. Okay, so this is for phi, which is velocity potential, u r cos theta plus with m over 2 pi ln r. Okay, so basically this is just a combination between uniform flow and source. Okay, so we don't have to derive how to get this psi for the source and uniform flow. Okay, it has been derived in previous lecture. Okay, so let's move for in next slide. Okay, so for some point along at axis, the velocity due to the source will cancel. Okay, so this the velocity due to the source will cancel due to the uniform flow, and a stagnation point will be created. Okay, stagnation point, you just remember that at stagnation point the velocity will be 0. Okay, at that stagnation point. Okay, and then for a source alone, okay, for this source only, we just recall to determine source, it is depend on strength of source or sink. It is m equal to 2 pi r vr. Okay, so source velocity in radial direction for the source and sink, it is equal to m over 2 pi r. Okay, and then at this stagnation point, okay, so basically this stagnation point we call it as this stagnation point. Okay, so we call at x equal to negative b, so we can define at this point. Okay, at this point u velocity radial is also equal to u. Okay, because it is cancelled due to the uniform flow, so u equal to m over 2 pi b. Or if you want to find what is the point for the stagnation point, b equal to m over 2 pi u. Okay, so this is how to determine the stagnation point. Okay, for this case. Okay, so move to next slide. Okay, so the value of stream function at the stagnation point can be obtained by evaluating psi stream function at r equal to b and theta equal to pi. Okay, so value of stream function at this stagnation point. So at this stagnation point, it is equal to by evaluating psi at r equal to b. So r equal to b and theta equal to pi. Okay, theta, it is equal from 0. Let's say this is 0, and then this is pi over 2, and then this is pi. Okay, so recall how to obtain the psi for this uniform flow. For this kind of superposition flow, it is psi for uniform flow. plus psi for source. Okay, and then psi for uniform flow, it is u r sine theta plus m over 2 pi theta. Okay, so at this stagnation point, it is r equal to b. Okay, r equal to b and theta equal to pi. Okay, so that 0, pi over 2 and pi. So u r sine theta, that sine pi, it is equal to sine pi equal to 0. So it will be 0 plus m over 2 pi, theta is equal to pi. Okay, so psi for stagnation point, equal to m over 2. Okay, so this is how to determine the stream function at stagnation point. Okay, since m over 2 equal to pi bu, the equation of streamline passing through the stagnation point is, okay, so where this equation is come from. Okay, so basically this equation come from the stagnation point. Okay, so before this stagnation point, we got u equal to m over 2 pi b. Okay, so m over 2. Okay, so m over 2 basically equal to pi b bu. So this is where we got pi b. M over 2 equal to pi bu. Okay, the equation of streamline passing through the stagnation point is, okay, so just substitute this equation, we get psi, which is equal to stagnation point. So psi stagnation point equal to m over 2, which is m over 2 equal to pi bu, not small u, it is capital U. Pi bu equal to u r sine theta plus with ub theta. Okay, so m to pi, m over 2 pi equal to u bu. Okay, so m over 2 pi equal to u b theta. Okay, so and then we can we can cancel out u because we have all u. Okay, so from this equation we can obtain r equal to b pi minus theta divided by sine theta. Okay, this equation. Okay, so r equal to b theta minus, b pi minus theta divided by sine theta. Okay, where theta, the angle can be varied between 0 to 2 pi. Okay, from 0, this is 0, this is pi over 2, this is this is pi, and then this is 3 over 4 pi, and then this is 2 pi. Okay, so this is how we can vary the radius r. Okay, so from this r, we can let's move to next slide. From this r, we can come up with a plot of streamline for this case. Okay, so as I shown in as was shown before, this the gray color basically it is represent a solid body. Okay, for where we have a uniform flow and then source and in between the uniform flow, so we got this kind of flow. Okay, so this is point of source and then this is the stagnation point. Okay, so for the streamline, okay, so for the streamline, it is defined as a pi bu. Okay, the streamline for this at this region, this solid body, it is equal to pi bu. So pi bu is from this equation. Okay, so streamline equal to m over 2, which is equal to pi bu for the stagnation point and the stagnation along the stagnation line. Okay, and then the width of this body or this solid body equal to pi over b, and then pi over b or also equal to 2 pi b. Okay, so if we replace this streamline with solid boundary, it clearly shows that this combination of uniform flow and source can be used to describe the flow around a streamline body placed in a uniform stream. Okay, so the body is open, so this is open at the downstream. Okay, at the end at the downstream of this figure, so that's why we call it as a half body. Okay, so from okay, so the width of the half body asymptotically approach 2 pi b. Okay, so 2 pi b, this one as I mentioned before, this is 2 pi b, and then this also can be written as y b pi. So basically this equation comes from r equal to b pi minus theta sine theta. Okay, so r sine theta equal to b pi minus theta. Okay, so r sine theta basically equal to y, so y equal to b pi minus theta. Okay, so let's say you want to find this position. Okay, at this position, the distance at this position, at this point, okay, y, so you can use this equation. Okay, so y equal to b pi b, which is this distance, b pi minus theta. So this theta basically it is from 0, this is 0, and then at this point theta is pi over 2. So you can find the point or the distance from 0 to y, or point at this coordinate along the solid body. Okay, so that theta equal to 0 or 2 pi, the half width approached by b pi. Therefore the velocity component on the half body can be obtained. Okay, so now we obtain the if you want to obtain the distance or the point at any the coordinate or at any point along the streamline. Okay, and then we can define the b from previous slide. We can find how to find the stagnation point, and then we can determine we also have determined the psi for the stagnation point. Okay, now we proceed to how to determine the velocity component on the half body. Okay, so for the velocity component for the half body, just recall your from the first from the beginning of this the slide for the earlier of this chapter, which is we define the VR for the source or sink. Okay, so VR basically equal to 1 over R d psi over d theta. Okay, and then V theta equal to negative d psi over d dr. Okay, since we have psi, okay, so we just differentiate psi. Okay, so before this psi equal to u r sine theta plus m over 2 pi theta. Okay, so differentiate with respect to d theta. Okay, so differentiate the psi of d theta, u r sine theta, differentiate sine theta, you will get cos theta. So this one will be, but don't forget you have 1 over r, so 1 over r 1 over r u r cos theta plus m over 2 pi, differentiate with respect to theta, so you will get m over 2 pi. Okay, so VR now equal to UR, so this one will be U cos theta plus m over 2 pi r. Okay, so this is how to determine the radial velocity. Okay, and then for the tangential velocity, we theta equal to negative d psi over d r, which is u r, you will get u sine theta plus m over 2 pi theta, no, so it is 0. Okay, so but don't forget you have negative, so v theta equal to negative u sine theta. Okay, so this is VR and v theta. Okay, so if we would like to find the velocity at any point within this within this streamline, so we can determine in terms of the magnitude of the velocity. Okay, so the magnitude, for example, magnitude of the velocity equal to v square equal to VR square plus v theta square. Okay, and then from this VR and v theta, so you will get u cos theta for the VR plus m over 2 pi r square plus negative u sine theta, okay, this is equal to u square sine square theta. Okay, so solve for this u cos theta m over 2 pi r power of 2, you will get after you simplify. Okay, so you will obtain u square cos square theta plus 2 2 pi r plus m over 2 pi r square square plus u square sine square theta. Okay, so for and then can simplify u square cos square theta plus sine square theta, okay, equal to plus u m cos theta divided by pi r plus m over 2 pi r square. Okay, so simplify. So this one from the trigonometric identities, it is equal to 1. So this one will be u square plus u m pi r cos theta plus m 2 pi r square. Okay, so this is magnitude of the velocity. Okay, so if you want to simplify, okay, so if you want to simplify, let's move to next slide. So it can be simplified because from this you can define in terms of B, you can define in terms of stagnation point. Okay, because from the previous slide you have defined the B equal to B equal to m 2 pi u. Okay, so you can simplify based on B equal to m over 2 pi u. Okay, and then after simplification you will get the last equation for the velocity equal to v square equal to free stream velocity u square plus 1 plus 2b over r cos theta plus b square r square. Okay, so this is the final equation for the velocity. In when for this case, for velocity around the half body. Okay, and then let's in the earlier of this lecture I explained about this kind of flow. It is inviscid. Okay, and then it is also irrotational flows because it is still in basic potential flow. Okay, so when we have the velocity, we can find the pressure. Okay, we can find the pressure at any point because we have the velocity. We can also we already have the velocity at any point. Okay, so to find the pressure we can use the Bernoulli equation. Okay, so you just recall your MEC 441 fluid mechanics 1. The Bernoulli equation the Bernoulli equation is for the irrotational, for the inviscid flow, and of course it is for steady flow and compressible flow. Okay, so let's say you want to find the velocity, you want to find the pressure, you just use the Bernoulli equation. Okay, so Bernoulli equation Bernoulli's equation. Okay, so for example it is P naught plus half rho u square equal to P plus half rho v square. Okay, so U squared is for uniform, V squared it is for this source, and for this V square. Okay, so you can define the pressure difference P naught or P at the outer part or at the some point far from the body. Okay, so if you notice that the elevation difference is not mentioned in this equation, because we assume that it is the P naught, it is really far from the body, so the change of Z is negligible. So that's why it is how this is where the Bernoulli equation looks like. Okay, and then this superposition plane between minimum flow and source provide useful information about the flow around the front part of streamline body, such as bridge, pier, or strut. Okay, and then an important point to be noted for this case, that it is only for this case applicable for potential flow, of course, and then it is for inviscid flow. Okay, for this case, the velocity tangent to the surface is not zero, mean that the fluid is slips by the boundary. Okay, but bear in mind this is only valid for inviscid flow. Okay, but ideal in the real flow, there are regions for a thin, very thin boundary layer, where it is in the region of viscid flow. Okay, so for this case, near the wall, for example, all potential flow do not accurately present a real fluid flow. However, outside of the thin boundary layer, the velocity distribution will generally correspond to that predicted by potential flow theory if flow separation does not happen in your analysis. Okay, so mean that this potential flow can be used if we consider when the flow or the cases does not have any flow separation. Okay, and then the pressure distribution also can be obtained along the surface, where it closely approximate that predicted from the potential flow theory, since the boundary layer is very thin. Okay, so for the next video, I will explain about Rankine flow, which is uniform flow plus with equal strength of source and sink. Okay, thank you very much.